Yeah, so I'm Daniel Firestone. I'm representing the work of many people across Microsoft, including in the Azure group and research. And we're going to talk today about the Azure Accelerated Networking service and how we use SmartNICs to accelerate networking in our public cloud. Is my clicker function? OK. So this is really part two of a talk that we gave last year at NSDI. Last year, we talked about the virtual filtering platform and our scalable host-based data plan, how we used host networking to scale Azure out to what it is today in software. Now we're going to talk about how we evolved that further to offload all of that to hardware. So I'm going to start off by talking a little bit, recapping Azure and scale and what host SDN looks like in our cloud. I'm going to talk about why we wanted to do accelerated networking in the first place and what scale for SDN means. I'm going to talk about some of the hardware choices that we had and some of the different options we thought through. I'll describe the Azure SmartNICs, and then I'll talk about results of the Azure Accelerated Networking service that we launched on top of it, and conclude with some experiences and lessons learned and some thoughts for the future. So, by way of reminder, Azure is Microsoft's public cloud platform with infrastructure services, IaaS, like compute, storage, and networking, data services on top of it. Looks like my clicker's going fast. And app services on top of that. You can build big data services and machine learning services, and we have a wide variety of platform services on top. General marketing numbers will tell you that Azure is growing quite fast. We are the second largest public cloud in the world. We've got 50 different global regions all over the world with hundreds of data centers, millions of servers, and this drives quite interesting scale problems on the network. So to recap from last year, so our software-defined networking stack is based on host networking. And our host networking component is called the virtual filtering platform. It's a virtual switch that provides all of our core network virtualization functionality, such as bring your own VNets, load balancing, NAT, ACLs, and it uses programmable rule flow tables to program per packet actions from controllers. In fact, it's programmed by multiple Azure SDN controllers, supporting all this data plane policy at line rate and with some offloads. As a basic example, we want to support here is that we have a match action table primitive that lets multiple different controllers running multiple different applications, for example, address virtualization, load balancing, etc., come program their own view of the network, which we call layers, or different flow tables in sequence, each of which can be stateful. You can have stateful NATs, stateful ACLs, and program per TCP connection policy. And then we're going to combine all those together into a single action for those flows that are coming through the network. And the basic way we do that is with a technology called unified flow tables, which is a just-in-time compiler for flows where we take the first packet of every single TCP connection or UDP flow that shows up in our system, run it through all the different complex policies we have, which may involve lookups to a controller if there's policy missing, and then compile that into a single action that we cache on that connection, which can be updated with reconciliation if the policy changes later, so that we have fast lookups and fast actions no matter how many policies or layers or flow tables show up in our system. This is actually the basis of what we want to try to offload to hardware in our system, because it's really going to be inconceivable to think about so many different flow tables, so many different tens of thousands, hundreds of thousands of complex wildcard, range rules, et cetera, showing up. But we can actually offload this hash lookup piece here. And so that's our starting point for thinking about acceleration today. So why are we doing this? So let me just show you some historical NIC speeds in Azure. When we started off in 2009 and first launched Azure, we were at 1 gigabit. That was a lot of fun. Software-defined networking was cool. We played around a little bit with virtual switches and added ACLs to them, et cetera. And we didn't have so many packets to process, and this was OK. A couple of years later, we started deploying 10 gigabit servers all over our network. A couple of years after that, we had 40. Now we have 50 in the network. 100 gigabits is coming pretty soon. This is amazing growth in network traffic on a per server basis. And the problem for SDN is that while we got a 50x improvement in network throughput here, we did not get a 50x improvement in CPU power to go with it. And so simply pushing more and more into software was going to become expensive at some point. So So this is the fundamental question we want to answer today. This host SDN mechanism worked great at lower speeds. What happens when we scale it up further? How do we make that work? Our traditional approach at Microsoft to scaling this out has been with ASICs. We've worked with network ASIC vendors over the years to accelerate many functions, including TCP offloads like segmentation, checksums, steering virtual machine queues on a per VM basis, or RSS to create multi-core scalability for the network. We've done offloads of encapsulation protocols like VXLAN and NVGRE into the NICs. We've done various direct NIC access like DPDK. We've even offloaded, in some cases, the entire transport layer with RDMA. And so the question we had to ask ourselves going into this problem was, is this a long-term solution to this problem of SDN? So here's an example of the classic ASIC solution that the ASIC vendors came up with to deal with network virtualization performance, which is single root I/O virtualization, which is a fancy word that the PCIe people use to say that they're going to virtualize the PCI bus and assign a virtual PCI function for each individual virtual network adapter into your VM and use the CPU's virtualization capabilities to allow the VM to speak directly to the network. You can post packets to the network, you can pull them from the network. They bypass the host stack completely. The performance of these are great. These started showing up around the time that Azure was starting off, actually, when people wanted to do this kind of acceleration at 10 gigs. The latency is great. It's near native. There's no host stack. There's no second interrupt to process or second packet processing stack. But where's the SDN policy here? When asked to put a policy in this effective switch that's now in the NIC, most of the NIC vendors said, well, we'll just put a straight L2 Ethernet bridge here because that's what the standard Hyper-V or VMware hypervisors are just doing by default in their vSwitch. And so obviously, this was a great starting point for thinking about what hardware offloads could do, but it wasn't going to get us to a complete solution that supported our SDN policy. In fact, SROV is a classic example of something we call an all-or-nothing offload. And we call it this because the latency, jitter, and CPU benefits don't actually just come from offloading the policy itself. They come from skipping the host stack in its entirety, which is to say, even if 99% of the actions that we were going to perform on a flow were done in hardware, and we had hardware that supported almost everything, but we had one action that had to be processed in software, and that action had to be processed on most of our flows, well, then that means we're going to take the cost of indicating all those packets up to software to do that, and our offload is shot to hell. And other examples of this are RDMA, DPDK. This is actually a pretty common pattern when you do things like kernel bypass, host bypass, etc. And it means we have to consider carefully how we're going to add new functionality to our hardware as needed over time. And the key question here is, how do we get the performance of a hardware solution with the programmability of a software solution? So what were the hardware choices we thought about? So within the silicon space, as you look at accelerators on the network, there are a few different ones that we can think about. So CPUs are a standard model. You can put a few cores on a NIC and write C code and process everything in software there. Everyone's familiar with the CPU model. You're pulling out instructions one by one and doing a load store architecture and running them against your packets. One optimization over this can be to use NPUs, which are kind of similar to the idea of GPUs, lots of small cores that can individually do network processing functions. It's more efficient than a CPU, but ends up in practice having lots of scheduling problems if you want to try to move your packets across all of this and do stateful processing. An ASIC is actually the most efficient way to implement a circuit like this, but you can't actually change it on the fly in any fashion. It's literally just a circuit that specifies out your policy. An FPGA, on the other hand, allows you to take that policy and build it into the same kind of circuit that you would do on an ASIC, but actually reprogram it. It's a field programmable gate array. And so you can get the efficiency of something like a circuit in an ASIC, but with something much closer to software programmability. And then the fifth option that we considered was, well, don't offload at all, but instead, let's just keep making SDN more efficient in cores in the host, e.g., use a pole mode DPDK-like approach. In practice, what we found is that this was still going to burn more cores than we actually wanted to do, and it was very hard to control the jitter of something running in a pure software stack as opposed to a hardware circuit because you're dealing with a scheduler, et cetera. The way that we think about CPUs versus FPGAs is that CPUs are really a form of temporal compute, where you're pulling instructions in one by one, and a lot of your hardware is pulling an instruction, executing it against whatever data is currently in registers, and then pulling the next one. Whereas in FPGAs, it's really a spatial compute function and much more parallel. It is pipeline parallel, where your instructions are effectively sitting in your circuit and hardware, and you're just streaming data through them. So you don't have any instruction movement whatsoever. And this is part of the intuition for why FPGAs end up being so much more efficient than CPUs in practice for this. So our solution here is the Azure SmartNIC, which is based on FPGAs. And relies on the observation that hardware is really needed for scaled perf and cogs at 40G+, but the ASIC cycle and time to roll out new hardware is really too slow to add new functions when we're innovating on SDN all the time. And so we do need the agility of something like an FPGA. Our FPGA is programmed using an API called generic flow tables, which I'll describe a little bit more, which is a language for programming SDN to hardware using connections and structured actions as primitives, as I showed you in that last slide before. So I got lots of questions about FPGAs and why we deployed FPGAs in Azure, so I wanted to answer very quickly a couple of the most common ones. First, aren't FPGAs much bigger than ASICs? Well, an FPGA circuit itself may be larger than an ASIC circuit, but if you actually look at the chip, more than half that chip is high-speed transceivers, memory, etc. And when you consider that the ASIC has to be programmable enough to, deal with different functions that come up, whereas the FPGA logic can just be the fixed function that you want, what we found in practice is that the FPGAs are not actually that much larger and that much more expensive than competing ASICs when you put them together for this network workload. Which also answers the question, aren't they expensive? Obviously, I can't go into our vendor pricing, but if you actually consider everything to just be silicon area, then when you're at the scale of millions of units as we are, then you're really just paying for the size of that silicon. FPGAs are actually smaller per unit performance than a CPU, and while they are a little larger than ASICs, that was a price that we were willing to pay for this kind of reconfigurability. Aren't they hard to program? Well, yes, if you're a software developer and you've only seen C before, then yes, an FPGA is going to look a little tricky to program. If you're a hardware designer, which it turns out there are lots in the world, and if you have the kind of resources we have and are willing to hire a few hardware designers who can think about pipeline parallelism, well then it's actually pretty straightforward to program these things in Verilog, and we haven't had any issue doing so. Code is actually not necessarily locked into a single FPGA vendor. You can port across Altera and Xilinx relatively easily. And these things are actually deployed at hyperscale. We've deployed them. Amazon's deployed them in their F1 offering. And so FPGAs are actually pretty data center ready. So coming back to our picture, this really completes the picture that we started of what that host SDN stack looks like. You have VFP being programmed by all these different controllers through a northbound API that program a southbound API into these different tables. VFP is taking the first packet of every flow, the first packet of a TCP or UDP connection, running them through all these tables, compiling that into a single flow, and then those flows are getting offloaded to the SmartNIC, which indicate all the packets directly to the VM and from the VM going forward, which is where the offload comes from. So let's talk about the results of this. The main result is that we have Azure Accelerated Networking. Azure Accelerated Networking offers the highest bandwidth VMs of any cloud so far that we know of. Standard compute VMs get up to 32 gigabits. You can even get a stock Linux VM to get 30 gigs on a single connection with Cubic. Low latency comes because we provide SRIOV into the VM. We've seen a 5x, to some cases 10x latency improvement. Sub 15 mics within tenants is now common. We have increased packets per second. We support DPDK inside the VMs to access this NIC directly if you want to build a high PPS network function virtualization kind of appliance. We're supporting up to 25 million today or 12 million forwarded, and that number is only going to go up going forward. And we've seen much reduced jitter and lots of improvements to many database and OLTP applications, big data applications, machine learning applications, and lots across both first and third parties. And there are more examples and more data about this in the paper. One of the most common questions we get as we publish these papers is, okay, I see different public clouds talking about these systems we've built. How do I actually think about comparing these? So I wanted to provide you guys with just some simple tests that we went and ran across the three major cloud vendors to actually see what happens when you compare hardware offloads versus other sort of strategies. And I should preface this by saying, this is one set of tests that we ran with just stock Ubuntu VMs on the latest Skylake VMs of the clouds. Your mileage may vary. In fact, these numbers were taken in November, and they all since changed after Spectre and Meltdown and kernel page table isolation started showing up in VMs. But this is a good starting approximation. This is what's in the paper. First is on VM to VM throughput. What we saw is that with the SmartNICs, we were able to achieve not only the highest throughput at 31 to 32 gigabits, but actually on a single flow, we were able to achieve that full throughput, and that's higher than anything else we measured on standard Skylake-based cloud VMs. In latency, what we saw is similarly the standard latency with nothing but stock settings and BusyPol enabled using SockPerf. This is using iPerf and SockPerf, standard open source tools to measure them, was actually less than half that of others. And we now support, as part of the DPDK preview, a user mode TCP stack. And in that stack, you can actually bypass the kernel as well. It just plugs into your standard application, wraps around the socket API. And with that, we're able to get between 5 to 6 microseconds in the latest Skylake. These are called FV2 series VMs on Azure. You can go deploy 2 of these yourself and see for yourself the latencies are pretty great. But most importantly of this, what hardware really provides is low jitter, because you're not dealing with a scheduler in any form. And so this is a comparison of the jitter results that we measured as well. And you see that that solutions that have more of a software basis start to spike up in jitter as you get closer and closer to the tail, whereas what we found is that the network stays quite consistent through at least about 4 nines or so. And this is just testing millions of pings back and forth between pairs of Skylake VMs for a series of time. So let's talk about experiences and lessons we learned. So the first real one is that serviceability is key here. Every part of the system can be updated: the FPGA image, the driver, that GFT layer, VFP itself, the PF or virtual function driver of that NIC, any one of which is going to cause that hardware path into the VM to go down. But IaaS requires high uptime and low disruption. So we can't just take the NIC device away from under the app. We can't go reboot the VM whenever we want to do servicing. So instead, we create a path to keep the synthetic virtual NIC that we already had up and running into the VM and transparently bond it in a way that the VM doesn't notice to that hardware path, so that we can, when an update event happens, we'll notify the VM about 5 minutes in advance or so if it wants to start to drain traffic off. But we'll fail over during that update path from the hardware path to the software path. The app sees the same NIC. The app has no idea anything happens. It just sees slightly less performance for a period of time. And then we can, this allows us to support live migration, for example. This is how we live migrate VMs or update the many parts of the host OS. We add support for this to Windows. We actually push this upstream into Linux. We push this upstream into DPDK as well, which makes DPDK a lot more cloud ready. One of our learnings was a huge amount of the effort to deploy AccelNet was in making sure all paths here are rebootlessly serviceable without impact. We made lots of changes using the FPGA since we even first deployed this system. TCP and protocol state machine changes, all sorts of forwarding and duplication actions, new SDN actions, accelerating the offload path, all kinds of line rate diagnostics and monitoring that we added on the fly. It was incredibly useful, we found, to have the FPGAs and have the ability to regularly, every few weeks, whenever we wanted to, go update our basic hardware image on the fly. I'm going to skip a couple of the lessons learned and go straight to the conclusion. You can find more of these in the paper. But the future work and the challenge I want to give all of you is that everything here that we've talked about is hardware acceleration of a software SDN function we already had. And so my challenge to the group would be, what new functions can we build now that we actually have programmable hardware as a base primitive? Programmable transport layers in hardware, QoS functions, security functions. There's lots we can do in this space that we never would have thought of thinking of software as our only primitive. So we end with one of the top questions in networking at this point. Do we do virtualization in software or hardware? Of course, both have their places. Even in our system, we're using hardware to offload the fast path and lots of software control over the slow path. But to be a little bit cheeky and plagiarize a TV show, I will say, one thing we found definitively in our results is that software is not hardware. Really, only hardware is hardware. And if you want the best performance in the cloud, there's no substitute for the real thing. And with that, I will remind everyone that we're hiring and open to doing collaborations. And we'd love to work with you guys in programmable hardware, and I'll take any questions you guys have. And I'd like to invite up on stage Andrew Putnam and Sambrama Munkor, who are the technical leads for hardware and software for this program, respectively, to answer any questions as well. Thanks, everyone.
Do we have questions for Daniel? So let me ask you,
Sure.
Since there are no questions, if you had to fire up the imagination of students to work on hard problems that are, say, 3 years out using this kind of hardware, what would those things be that you'd like to see that would be useful, say, 3 years down the line? If they started working now, it might become something, ready to be used in like a production environment.
Sure. I'll start, and maybe I'll pass it around a bit as well. I would say the transport layer remains, in particular to me, remains mired in this either all software or all hardware approach. We have RDMA-based systems for storage that are really scalable but not programmable at all. We have software transports like TCP that look increasingly difficult at 100G. I think thinking about how we can change congestion control and the transport layer at that scale is to me actually one of the most interesting problems, because we're going to have 100 gig NICs, we're going to have 200 gig NICs within 3 years from now, and a bunch of the software techniques we have today just aren't going to scale. So I would definitely think about some of those.
I guess I would say, the hardware platform's been very stable for a long number of years, and now with the network speeds going up, 1 gig to 40 to 100 to 400, now you're also going to see the memory hierarchies changing a whole bunch, and lots of the assumptions about just what systems look like and what the whole system the whole computing environment as a whole look like are going to change. And with this kind of programmable hardware, you can keep measuring and changing that stack kind of on the fly. And remember that these we're deploying hundreds of thousands and millions of these things, and they're going to be around for longer and longer. And so you have to not only think about what new functions can you add now, but how can you prevent every user of your cloud from always having to upgrade their VMs every time they want to add some new feature.
I'd like to say that, first of all, it's really a cool technology, because it's really fun to see that what we want to develop in software, we can offload to hardware almost within our, literally sprint planning, so it's really fun to do that. But we also have to think in a way always of coexistence, because it's not just about developing software, developing hardware, because you need to be able to understand what are the limitations and benefits of each other, and sort of co-design.
Okay. Hi, I'm Yan Fang from University of Wisconsin-Madison, and actually because this is the last talk of this session, so I have a question about the hardware offloading stuff. So, like the net cache, that SOSP paper and the first paper, and we see that there are a lot of constraints or capability, limited capability in current hardware. So we are publishing paper trying to overcome this hardware. And even like the RDMA, people says we use the PFC to enable the lossless network. But if we can implement the retransmission protocol, we don't need the PFC. Something like this. So what's the hardware offloading research direction? Because I think this kind of constraints can be solved in maybe a couple of years, right? So why do we still need to propose such so many people to overcome this kind of small limitation? That's my big question about it.
Sure. That's a great question. I would say the example you gave around PFC and lossless networks and retransmission is a great example of something you can do if your transport layer in hardware like RDMA is programmable, which is what we're talking about here, is building programmable hardware. You may actually still want, for example, some lossless capabilities there because you don't actually want the latency for storage systems that tail drops implies. But as those workloads keep changing, you are going to keep modifying those protocols. And so what we think is one of the most important directions to emphasize here is that whatever your hardware architecture is, it has to be flexible and programmable for new applications and workloads.
So we'll take one last question, Harry.
Hi. Harry Liu from Alibaba. Great talk and great work. So my question is just like this session, right? I think people realize we want to put things into hardware, but there are two directions. One is putting things in network. The other is to do things in hosted networking. So I want to ask your opinion about this. So based on your experience in cloud, so will the hosted networking hardware offload will be enough for everything, or is there anything you find that you have to do it in network? Thank you.
So the question is about what can be done in network versus in the host. I would say the switches are a little bit inherently limited by the table sizes that you can put there, the fact that everything has to be in SRAM. We've gotten top-of-rack switches at 6.4 terabits and going well past that. So you're always going to be able to put more stateful policy in the host. That doesn't mean you can't do interesting things in the switches as well, but we have found the hosts a little more scalable, a little easier to add this kind of functionality to in hardware.
There's also a certain amount of monitoring and diagnostics and things that you can really only do at the host level. And when you add this, when you add it at that, you're going to get a much more complete view of the network. And so I think there's still going to be a lot of good work to do in the network and the switches. We have the Sonic program, which we also participate in, do a lot there. But you're going to need to have that kind of programmability on each level of the stack.